So, welcome friends. In this lecture we will continue our previous lecture which was on the linear quadratic optimal control system problem. We are trying to find out the optimal control law for a linear quadratic regulator problem. In linear quadratic regulator problem, what we are doing we are given with the system x dot equal to a x plus b u y equal to c x. Objective is to determine the u which will take the plant from non-zero state to a 0 state and simultaneously minimize a performance index which is given as x prime t f f of t f x of t f plus half of x prime q x plus u prime r u. So, this problem we are solving using the Hamiltonian approach. We first define our Hamiltonian H, we take del H by del u equal to 0 which gives the u equal to r inverse b prime lambda t. Then we define our Hamiltonian system x dot equal to a t minus e t minus q t minus a t x lambda. So, this means x dot and lambda dots are represented in terms of the x and lambda. So, we have the n by 1 state vector, n by 1 co-state vector. So, total dimension of the system is 2n by 2n. This Hamiltonian system along with the terminal condition we have taken as the lambda Tf as f of Tf x of Tf. So, we have to develop a state feedback system, and if you will recall my u is nothing but r inverse b prime lambda t. Lambda is a unknown quantity. So, this means we cannot directly feedback my system. To get the feedback I have to relate my u with x, but to develop the relation between lambda and x lambda t and x t, we can take the intuition from the lambda Tf as f of Tf x of Tf. So, we assume a transformation which will give me lambda t as pt xt, where pt is a unknown quantity. We have to find out the value of the p. So, if lambda is pt xt, then ut I can simply write as minus r inverse t b prime pt xt. So, this means if I know the x I can determine my r inverse b prime p, so I can feedback. So, if you will recall in the previous lecture in a linear quadratic problem my control law was the u equal to minus kx. So, this r inverse t bt pt will be nothing but by k. So, by this transformation I can transform my system in a simple linear feedback system. So, this negative feedback of the state xt I can give to use it as my control feedback. Now, from my Hamiltonian system I have xt as ax minus br inverse b prime pt xt and lambda t as minus qt xt a transpose pt xt. Transformation we have considered as lambda t as pt xt, we have taken as lambda t pt xt. So, if I will differentiate this, equation, so I will get lambda dot t as p dot t xt plus pt x dot of t. So, I have equation lambda dot t as pt xt plus p x dot t, and x dot and lambda dot value I can write in terms of my Hamiltonian equation. So, in this Hamiltonian equation if you will see I have the x dot in terms of the xt, and if you will see pt xt is nothing but my lambda t. So, from this relation I have replaced a lambda t by pt xt. With this I am writing these two relation as ax minus b r inverse b prime px and lambda dot as qx a prime px. So, this means I am representing x dot and lambda dot both in terms of the x. Now, in lambda dot t equal to p dot x plus px dot, I am substituting the value of the lambda t and xt, which will be, so what is my lambda dot t? Lambda dot t is q minus qt xt minus A transpose PT xt minus A transpose PT xt. This is my lambda t. This I will keep as such, P dot t x of t plus Pt, and x dot of t is Ax Atxt minus, sorry, I have B R inverse B transpose T xt. So, I have substituted x dot and lambda dot in place of this lambda dot and x dot. This is minus qt A transpose P xt, and this side what we have, P dot plus PA minus P B R inverse B transpose this will be B transpose, sorry, here I have directly written the xt, but this is D transpose PT xt. So, this is B transpose PT and x of t, and this x of t we can cancel out and write the whole equation. On one side we have P dot t plus PT AT, second term I am writing here A transpose T PT minus P B R inverse B transpose T PT plus Qt equal to 0. So, by this we got this equation P dot T plus PA plus A transpose P plus Qt minus PB R inverse B prime PT equal to 0, and this relation should satisfy for all, for my specified time T0 to Tf, and for any choice of my initial condition x T0. So, this means I have to solve this equation to get the value of the P, and as we can see this is a differential equation which can be solved using my terminal condition, which is lambda Tf as Ptf xtf equal to f of Tf x of Tf. This means Ptf is f of Tf. So, this is the matrix differential Riccati equation. This has to be solved backward in time and using the final condition to obtain the solution Pt for the entire interval T0 to Tf. Once I know the Pt, then directly I can write my u, which is nothing but minus R inverse B transpose, now it is Pt into x of t. So, this is my u, ut, which I am directly writing as, this implies ut is minus kt x of t. So, k is nothing but R inverse B transpose T Pt. So, for a linear quadratic regulator system, I have to find out the value of the Kt, which is R inverse B transpose Pt, and Pt is nothing but the solution of my differential Riccati equation DRE, and this DRE can be solved using the final condition as my Ptf equal to f of Tf. So, in backward we can solve this Riccati equation to get my Kt. So, directly I can apply the ut as my complete state feedback. So, I can measure the xt multiplied with the Kt and give it as my u. So, this will solution of this matrix DRE is a non-linear differential Riccati equation. So, the numerical technique can be adopted to solve this, and for a simple system we can directly have the solution of this Riccati equation. So, we will see it in form an example how this can be, or how we can determine the optimal control law for a linear system. So, we take an example. Let me change this pen. So, let us consider a first order system as x dot t two xt plus ut. Consider a system. My objective is to find the optimal control law that minimize my j equal to and in this case my T1 is specified. So, my problem is for a first order system we have taken as x dot as 2x plus u, we have to obtain the optimal control law which is minimizing my performance index given here in a specified time t1. So, t1 is specified in this case. So, now if you will see what is my terminal condition, my terminal condition here is because no terminal cost is given. So, this means f of Tf equal to 0, my control law is u equal to minus ut equal to minus kt xt and kt is minus R inverse B transpose pt xt. So, now with this if I will write what is the different values. So, before that if we will see to find out the this is my u of t and this is my kt. So, ut can be determined and pt is the solution of my differential Riccati equation which is given as p dot t plus pa plus A transpose P minus P B R inverse B transpose P plus Qt equal to 0. Now, if you will see what is my A, 2xt, so A is 2, B is 1, F is 0, Q is 3 and R is 1 by 4. So, if I will substitute these values into this, all these values in this equation, so what I will get? I will get a final equation I am writing here as P dot T minus 4 P square T plus 4 P of T plus 3 equal to 0. So, this differential equation I have to solve with, and what is my condition? P Tf is nothing but 0 because f of Tf is 0. With this condition I have to solve this equation. So, it is a simple first order differential equation which can be solved. So, I am writing this as P dot dP by 4, just for simplicity I am dropping the t terms from here, 4 p square minus 4 p minus 3 if I will take it there, and this is nothing but my dt. This I will integrate from t to t1, t2, as t1 is final time. So, I can write this p t1 as 0, because f we have taken as the t1. So, there are many approaches to solve this. I can make the factors of this, then directly take the integration. I will integrate this. So, this you can perform the calculation yourself, and its final solution I am giving you. With this, if I will calculate, my PT comes out to be 3 by 2 1 minus e to the power 8 t minus t1, the whole divided by 1 plus 3 e to the power 8 t minus t1. So, this will be my PT, and ut is nothing but minus r inverse b prime p, which is coming out to be the 4 PT xt. So, this means my kT is nothing but 4 and PT, and this PT we already have been determined here. So, this will give me my final control law. My ut is minus 4 PT xt and my kT is 4 PT. So, in this way we can find out the solution of the matrix differential Riccati equation. For a first order system, I have only the single equation, but if as the order of the system will increase, the number of equations will also increase. So, we take the another example as x1 dot t, x2. So, we consider a second order system with initial condition as x1 0 as 2, x2 0 as minus 3. Our objective is to determine the optimal control law ut, which will minimize the performance index j given here. So, we can see in this example we will have the terminal cost as well as my integral cost. So, to solve this problem, if we will see, so what will be my ABCD? My A is 0 1 minus 2 1, BT is 0 1, FT which is given here, QT 2 3 3 5, RT is 1 by 4 and T0 and the TF are specified as 0 and 5. So, TF we have taken as the 5 and starting point is T0, initial point is specified. To determine the U, we have to write our Riccati equation. P dot T equal to PA plus A transpose P minus P B R inverse B transpose P plus Qt equal to 0. So, in this if we will put the value of A, B, F, A, B, Q, R, because A, B, Q, R is required here. So, my equation will be, so now what actually will be my P? for a second order system, I consider my PT as P11 of t, P12 of t, P12 of t and P22 of t. So, we have considered this matrix as a symmetric matrix. So, P is a symmetric positive definite matrix. So, in the next class we will discuss why P is a symmetric matrix. So, just for our consideration we take this P as my symmetric matrix here. So, with this value of the P and the value of the A, B, Q and R this, I can write my equation as P11 dot, P12 dot, P12 dot, P22 dot as this whole equation. So, now if you will see, because this is a symmetric matrix, so in place of the 4 I will get only the 3 equations and these 3 equations. So, now if I will simplify this matrix I will get these 3 equations, P11 dot in terms of the P12. So, this is a interrelated equations, but I have to solve this equation for the P11 dot, P12 dot and P22 dot to get the value of my P matrix as this. So, these equations with my final condition as P115, P225, which I am getting nothing but from my matrix F. So, this F matrix means my PTF equal to F of TF. So, all these parameters will represent here as the final value of my P11, P12, P12, P22 as 1, 0.5 and 2. So, these 3 equations I have to solve with these 3. Any numerical technique can be adopted to solve this equation, and by this way we can determine the P matrix. If P is known to us, then we can find out the K. If K is known to us, we can find out the U, which will be U equal to minus K T and X of t. So, in this way we can solve our linear quadratic regulator problem for a finite time. If TF is finite, then matrix differential Riccati equation we have to solve. This matrix differential Riccati equation we have to solve to find the value of the P, and once the P is known we can find out the U. So, this class I stop it here, and in the next class we will discuss about the infinite horizon, time varying and the time invariant case. Thank you very much.